Fusion is another nuclear energy process. Unlike fission, which takes place with very heavy nuclei, fusion happens with the lightest. A simple fusion process might be to take 4 hydrogen nuclei, shove them together and make a helium nucleus. This won't work because of the positive charge of the protons. It would just fly apart. A better way might be to combine 2 deuterium nuclei. These nuclei contain 1 proton and 1 neutron, so they have the right numbers of protons and neutrons to start with. However, combining 2 deuteriums doesn't automatically make a helium nucleus. It can make a helium, helium-3, and a neutron, or it can make a tritium and an ordinary hydrogen, tritium being 2 neutrons and 1 proton together in a nucleus. The third way is to combine a deuterium atom with a tritium atom, or their nuclei. This gives us 3 neutrons and 2 protons, so more than enough to make 1 helium. In fact, it does make 1 helium, a helium-4, the right kind of helium for us, and a neutron all by itself. First things first, let's calculate the binding energy of helium. It's kind of just for fun, but there is a point. The binding energy is the energy required to separate the protons and neutrons in a nucleus, so they are just protons and neutrons, and not a helium nucleus. The energy is really simple to calculate. All you need to know is the mass of a proton, the mass of a neutron, and the mass of a helium nucleus. A proton has a mass of 1.0078 U. That's atomic mass units. A neutron has a mass of 1.0087 U. And a helium nucleus has a mass of 4.0026 U. A helium is made up of 2 protons and 2 neutrons. Separately, they have a mass of 2 times 1.0078 U plus 2 times 1.0087 U, which equals 4.033 U. That's 0.0304 U difference. This mass, when converted into energy, tells us the binding energy of the helium nucleus, and it's equal to 28.3 megaelectron volts. Just take the 0.0304 U from before, times it by 931.3 megaelectron volts, as we discussed in a previous podcast, and you get your 28.3 megaelectron volts. You would need to add this energy to any helium nucleus to break it up into just protons and neutrons. It is not the energy produced in the fusion process. That is the difference between the energies of the initial elements and the energies of the final elements of a fusion reaction. Just like in a chemistry experiment. So let's talk about that. Deuterium and tritium are the isotopes of hydrogen. Deuterium can be found in the places you would find hydrogen, but in much lower levels than ordinary hydrogen. Tritium would need to be manufactured as it doesn't naturally occur. The binding energy of deuterium is 2.224 megaelectron volts, and tritium is 8.481 megaelectron volts. You would need to add these energies to deuterium and tritium to break them up. So the total energy involved to start the process is the mass energy and the binding energy of deuterium and tritium. This equals 4695.284 megaelectron volts. The binding energy for a helium-4 nucleus is 28.3 megaelectron volts. Combining this with the mass energy of the helium and the neutron gives an overall final energy of the final side of the equation of 4695.288 megaelectron volts. The difference between the initial stage, the initial total energies, and the final stage, the final total energies, is 0.004262 megaelectron volts. This is extra energy generated through one deuterium-tritium fusion reaction. Comparing that to fission will be done in the next podcast.